Hey everybody, it's Ripley back again. So some of you are starting to already get a hankering for these antiderivatives and that they roll into integrals, and you may have heard, pray tell, that there are rumors afoot that the area under a curve is somehow related to integrals. So what I'm going to do is we're going to talk about the area under a curve, but I'm going to talk about why the area under a curve is important, or why people even started playing around with the idea back in the day. Okay, so just think about it. It's actually quite simple, and it falls out perfectly from differential calculus. If I look at, it's going to be the easiest thing you ever saw. All right, let's say that I go 60 meters per, I don't know, minute. I don't know what that means. And then t over here is equal to minutes, and this is going to be, let's see, I'm sorry, this is v of t. Now, people understood that if you had a curve and you found the area under that curve, well, let's keep it as simple as possible. I'm going to go 60 meters a minute for 10 minutes. Now, your brain's already going, Ripley, I already got this. This is easy. And you're right. It is easy. But think about the ramifications of this, okay? You already know that you've gone 600 meters in 10 minutes. So it would be 600 meters per minute times 10 minutes, right? Minutes cancel and you end up with 600 total meters, right? Well, think about that. This is a velocity function. So when you got to remember that most of calculus came out, both differential and integral, and by the way, this is sort of an introduction to integral calculus, when both calcula came out of ideas about physics and about motion, like rectilinear motion. We talked about that. And people said, whoa, okay, if I can, in the superlinear sense, if I can figure out the total distance that something travels by taking the area of this rectangle, well, what would happen if the velocity function didn't look so pretty? What if it went something like that, right? If this were still v of t, then the area under the curve would still represent the total distance traveled. So people started thinking, hey, wait a sec. We need to be able to figure out the area under the curve because this may have all sorts of ramifications, particularly, excuse me, in physics. But let's keep it simple. All right, we're going to go nice and easy. Hopefully I have planted the seed of, oh, wait, perhaps the area under the curve has uses, and maybe even more uses than just going from velocity to total distance traveled, right? All right, so what we're going to do is we're going to take a very systematic approach to this. And the approach was first systemized by a mathematician by the name of Riemann or Riemann. All right, I don't know if it's a diphthong, whatever. Okay, and what he came up with was he's simple country folk, just like all of differential calculus was built on slopes of lines, right? He was like, all right, why don't we start with the easiest known area to find, period. We've been doing this for forever, all right? So we're going to start with what's called a left Riemann sum. Left Riemann sum. And there's some notational obstacles we got to get out of the way. Sometimes you will see this as a left rectangular approximation method. So that would be left rectangular approx, depending on your textbook, method, which is which is written as LRAM. But if it's written as L, right, with a subscript here, then you know that it's a Riemann sum. That's sort of the conventional notation. So what we're going to do is we're going to do 1, 2, 3, 4, 5, 6. We're going to do L sub 6 on this function. And what Riemann said is, hey, let's just start with rectangles. What I'm going to do is I'm going to start on the very left-hand side of this interval, right? However, I'm assuming that this interval goes from 0 to 1, 2, 3, 4, 5, 6, 0 to 6, and we're going to divide it up evenly. Now, something that is very important in this type of calculus is something called delta x, or the change in x. And delta x is really simple. And Riemann said, okay, I can do this, but I would prefer, I'm not necessarily guaranteed, but I would prefer to have all my changes in x. In other words, all the widths of my rectangles be uniform, be the same distance. So what he said was, okay, in this case, we would just go 6 minus 0 divided by 6, and I get 1. And in general, if this were an A and this were a B and you could hand me any number that you wanted, let's say that instead of L sub 6 we wanted L sub 20, what we would simply do is we would say B minus A divided by N. This is your best friend. B minus A over N is delta X, and we use it to the hilt, okay? All right, now watch what happens here. What we're going to do is we're going to start on the very left hand. Let's assume that this function actually hits at the origin. We're going to start at the left-hand side of this first subinterval. This subinterval is delta x wide. It's referred to as a subinterval because we typically would say on the interval from 0 to 6, right? We've done that before. Closed interval, open interval, stuff like that. So this is a subinterval. We just took a little subset of it. Again, all of these are delta x wide, et cetera, et cetera, et cetera, delta x wide. So he said, okay, the first one is going to be a rectangle that starts on the very left-hand side. So in this case, it's actually a rectangle of no height, right? So what we do is the L sub 6, which is approximately equal to the area, right? So we'll go L sub 6 is equal to, well, we've got delta x wide times f of 0. And that would give me the first rectangle. And I know you're going, Ripley, why are you wasting my time? The first rectangle doesn't have any area. Well, that's cool. It'll show up mathematically, right? We're not afraid. And then he went, okay, let's start at the left-hand side of the next subinterval. And we're going to draw another rectangle right there. All right? And then, remember, this is 1, and this is 2, and this is 3, and this is 4, and this is 5. Sorry that I drew those in with the delta x's. That looks a little confusing, but I think you can figure it out. Hopefully you didn't pick up the video right in the middle. So the next one is going to be delta x times f of 1, right? Because I moved over to the left-hand side of the subinterval that went from 1 to 2. I went up to f of 1. This point right here would correspond to 1 f of 1, right? You could probably see how systematic this is. I would go plus delta x, go up here, and then over, and then down. Delta x times f of 2. Again, 2, I use the f of 2 because it's on the left-hand side of the subinterval, plus delta x times f of 3, et cetera, et cetera, et cetera, plus delta x times f of 4. I'm going to run you guys through this just on this first one, and then I'll start using ellipses to cheat. So f of 5. Now wait a sec, we got to check. I'm getting a little crazy here mathematically. Remember, I wanted 6 rectangles to approximate the area. So I've got 1 rectangle, even though it has no area. 1, 2, 3, 4. I'm going to do 2 more, 5, and 6. Now if you notice, I'm not going to go over to 6 because if I go up to 6, then I have to build a rectangle where I didn't want to find the area. Now, I know there's a great hue and cry and gnashing of teeth right now going, Ripley, it is blatantly obvious. This is ridiculous. It is obvious, excuse me, that we have an under-approximation. This is blatantly going to under-approximate. So Riemann said, okay, fine, suit yourself. We're going to do R sub 6. All right? So again, R sub 6, approximately equal to the area. But what does R sub 6 equal? Well, we still have a delta x of b minus a over n, or 6 minus 0 over 6, which is 1. But this time what I'm going to do is I'm going to go over to the right-hand side, and I'm going to cruise over, and I'm going to build myself a little rectangle. And then the right-hand side, cruise over, right-hand side. Now settle down. I know what you're about to say, but just relax. Now notice that we're actually going to pick up, instead of starting at 0 and going to 5, we're going to start at 1 and go to 6. So R sub 6 is going to be delta x. Now, you also were probably thinking, Rip, why didn't you just pull out the delta x's? Well, because it was the first example. You guys should just cool your jets. So in this case, it's going to be delta x, and then this is going to be f of 1 plus f of 2. Now, since they all have delta x's, since all of the rectangles are delta x wide, I can factor it out, and I get plus f of 3, and then plus dot 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 plus f of 6. And that picks up, as you're probably already seeing, way too much area. So if we think of this as Goldilocks and the three bears, the light blue is a little too small. The dark blue is a little too big. So of course, what did Riemann say? He said, you know what, let's go for the midpoint. And the midpoint, whoops, 6, and the midpoint, which is approximately equal to area, is going to be probably the sweet spot. It's still not going to be perfect, is it? And we'll discuss ways to make it perfect, but it's still not going to be quite there. But we will discuss ways in just a sec. You ready? Boom. What we do is we go to the middle of the subinterval, we go up to the curve, and we draw ourselves a rectangle. Middle of the subinterval, up to the curve, draw ourselves a rectangle. Middle of the curve, middle of the interval, up to the curve. Whoa, what are you doing, Ripley? It's a little late at night. I snuck in late to get some work done. Middle of the interval, up to the curve, middle of the interval, up to the curve. Now look at these. This is kind of nice, isn't it? Let's pick a big one so you can see it. Look at this. I'll actually draw in the rectangles. And, oops, right there. Now look at this sort of penultimate one, the second to last one right here. If you'll notice that this guy right here is too much, and this guy right here is too little. But if they sort of cancel each other, don't they? Which gives us sort of an overall yay smile, which is kind of cool. So how would we represent this? Because we're not picking a value on the left-hand side or the right-hand side of the subinterval, the way we say this is we say delta x, and then we go f of x bar 1, which is the middle of the subinterval, right? It's like, think of the mean. If I want the mean of the subinterval, I would take the sum of the left and the right, and I would divide by 2. So we say the mean of the subinterval plus f of x bar sub 2 plus f of x bar sub 3 plus plus f of x bar sub 6. And I'm off to the races. Okay? Now, just think about it for a minute. If you really wanted to be able to find the actual area, like what would I need? Let's change colors. What would I need to be able to determine the actual area under that curve? How would I do that? It's pretty easy, right? What would I do with my number of subintervals? What would I want to happen to the width of my subinterval? I would want the width of my subinterval to shrink so close to 0 that each one of these rectangles would just be filling in the curve, right? That would be the sweet spot. I get all these teeny tiny little rectangles that fill in the curve. So what am I going to do? What I would do is I would simply let the limit as n goes to infinity of L sub n, which if I let n go to infinity, wouldn't that be exactly the same thing as the limit as n goes to infinity of R sub n, which is the limit as n goes to infinity of m sub n. All right? Now, this can be written in a really, you're going to be like, oh, I don't like the way you're writing this, Ripley, because it's got really weird notation. But that's okay. No freaking out. It's actually pretty easy to be able to work this out. What this is going to equal is delta x times, and then because I can kind of arbitrarily choose a left or a right or a middle, what we simply say, just to kind of make our lives easier, is we say this is going to be f of x star. And the star just means, hey, pick your poison. You can pick the left, you can pick the right, you can pick the middle. Heck, you can pick 2/3 of the way over or 1/10 of the way over. It's up to you. It doesn't really matter, because as long as I let the limit as n goes to infinity of these partition values go to infinity, I said infinity twice, didn't I? You're golden, because you get this same, you get this same fill-in of the area under the curve. But the way I write this is f of x asterisk or x star 1 plus f of x star 2 plus f of x star 3 plus ... Now I can't go f of x star 6 because I'm saying, hey, we're going to let the number range out to infinity. So we just say f of x star n. And guess what? You're set. Okay. Now another way to write this guy is you could actually, if you recall, we could actually write this thing out as, excuse me, we could write this as the sum as I goes from 1 to n of f of x star n delta x. Now we're getting fancy. We're starting to use some of that pre-calculus summation notation stuff that we like. It compacts everything down. And you may be like, Ripley, wait a sec. How are these two things equal? Well, watch. Put an I equal to 1. Whoops, that should be an x sub I, not an x sub n. Sorry, that's an x sub I. Whoops, right there. If I let I be 1, I get f of x star sub 1. If I let I be 2, I get f of x star sub 2. If I let I be 3, f of x star sub 3, etc. And I get exactly the same thing. What should I do with all those values? Add them up, and I'm golden. Okay, this typically is not a very difficult section in most textbooks. It's arduous, it's onerous. It's no fun. And the reason we make you do it is because we had to do it. I mean, really, I don't have a better excuse than that. Like every mathematician ever who learned integral calculus had to go through this process and actually had to do these types of summations by hand. Now, what your instructor is going to do, if you were in my class, I would say, okay, you get to use sort of this shorthand notation after you've done one in its entirety by hand. Because it's good practice. They have a tendency to show up on AP exams or credit by exams at the university. So I want you to have seen the notation, gone through the arduousness of actually having to do one, and then after that I let you trim it down a little bit. But I do leave that up to the prerogative of your teacher, because chances are your teacher ain't me. All right, cool. I hope you enjoyed the lesson, and I'll see you in the next section.